Okay. So we're looking at parent functions and translations today. All of these functions, hopefully you have seen. There might have been two, depending on when you have Math 3, if you got to them or not. But let's look at them. So our first one is just a constant function where y equals c. And so if it's just y equals a number, it's just a horizontal line. So we'll say that c is like right here. And so if it's constant, it's just everywhere where y equals c. And that would be the point 0, c. And so if it is a constant function, it's going forever to the left and forever to the right. So the domain is negative infinity to infinity. Because you have nothing stopping you there. You have no bounds, nothing. So it goes on forever. But for the range, since it's horizontal, it's just a constant. All of the y values are the same. They're all this c, whatever c happens to be. So for your range for a constant, it's just y equals c. So whatever that number is. Okay. So if y equals is horizontal, what kind of line do you think x equals is? What's the opposite of horizontal? Vertical, yay, thank you. So we have a point here. We'll call this one C. And it's just a vertical line. And so this would be the point C0. And so in order for a function to be a function, that means that every x value has a unique y value. Well, that's not the case here, because here my x is c, but yet I have every single y value imaginable. So this one is actually not a function. So we don't have to worry about domain and range for it. So our next little straight line is a linear. So y equals mx plus b. Maybe you remember that m is your slope and b is your y-intercept. But as far as the parent function goes, with no what? No, I can't think of the word. Now my video is messed up. Oh well. Is y equals x. So no add, subtracting, multiplying. It's just y equals x. And that graph crosses through the origin. And then the slope is 1, so up 1 over 1, up 1 over 1, up 1 over 1. So it goes like this. And then for this one, it goes forever to the left, forever to the right. It goes down forever, it goes up forever. So your domain and your range are both negative infinity to infinity. Questions so far? So with quadratic, those are the ones that we looked at last week when we played the game. So the parent function is just y equals x squared. And it crosses through 0, 0. Remember that point is called the vertex. And then it makes our little u into a parabola. And then for a parabola, your domain is always negative infinity to infinity. Whether it's opening up or it's opening down, it's forever to the left and forever to the right. But if we look at the range, how far down does the graph go? What's the lowest that it can be? Yeah, so right here, and my vertex, which is at 0. Yeah. So we want to bracket because it's at 0. But then it goes up forever. So infinity. Okay, so our next one is an exponential, and I put y equals a to the x, but of course a is a number, any number other than 0 or 1. But anytime it's an exponential, it's like that last one that was on your worksheet. So it kind of wraps around the x-axis. It doesn't actually cross it, and then goes up like that. And it has a y-intercept at 1, so the point 0, 1. And that's the case no matter what a is. If a is 2, if a is 3, if a is 100, your y-intercept is going to be 1. As long as you don't have any adding or subtracting. So then for our domain, we have two arrows. One's going to the left forever, one's going to the right forever. So negative infinity to infinity. And then for the range, even though it has an arrow on that side, it has what's called an asymptote. So when you have any number raised to a power, it's never going to be a negative number. It's either going to be a really tiny decimal or, a bigger number. So it gets super close to the x-axis, but it never actually touches it. So our range is from 0 to infinity. And we want to use a parenthesis with that 0 because, again, it never actually equals 0. Just gets super close. And so for a logarithmic, it is an inverse of an exponential. And so instead of crossing at 0, 1, it crosses at 1, 0, and it goes like this. So it wraps around the y-axis. And has an x-intercept at 1, 0. And so in this one, you can never take the log of a negative number or 0. So these domain and range kind of flip for this log. So our domain is from 0 to infinity. But then for our range, it is going up forever, down forever. So negative infinity to infinity. Questions? Y'all remember all these graphs, or at least kind of seeing? Yeah, good. Okay, so a cubic or an x to the third also crosses through 0, 0. And it kind of makes a little S kind of shape. So it kind of goes like this. And then if we look at domain and range, does it stop in any direction? Is it going left forever, right forever, down forever, up forever? Yeah, so it keeps on going. So negative infinity to infinity for both of these. So an absolute value is the exact same thing as a parabola. It starts at 0, 0, but instead of being a U shape, it's a V shape. So I always think absolute value makes a V. So it starts with a V and it makes a V. And then just like our parabola, forever to the left, forever to the right, but it does start at 0 and goes up only. So our domain is negative infinity to infinity. But we don't have any negative numbers here because remember, absolute value is the distance from 0, and distance is always positive. So from 0 to infinity. Okay, so these next two are the ones that maybe you saw, maybe you didn't see, depending on when you had Math 3 and what you got to if you had it in the spring. But a rational is, as you can see, 1 divided by x. And you know when you are dividing that you can never divide by 0. So these have what are called asymptotes. And so if it's just 1 over x, those asymptotes are the x and y axis. And what those are is they're vertical and horizontal lines that the graph will get super, super, super close to, but it'll actually never cross them. And as you start adding and subtracting, those things kind of move around the graph. And so what the graph actually does is it wraps around the corners like this, in the top right and in the bottom left. And then for the domain and the range, if you look at these graphs for your domain, it is going forever to the left and it is going forever to the right, but it never actually equals 0. So how you write it is you can say negative infinity to infinity, but then you have to say where x does not equal 0. So you can write it that way. You can do the two separate intervals, like from negative infinity to 0 and then 0 to infinity, and it works the same, but this is just a little bit easier. So all real numbers except for 0. And then same for the range. It goes down forever and it goes up forever, but it does not touch 0. So negative infinity to infinity, but y cannot equal 0. And again, that's because your x is in the denominator and you can't divide by 0. Okay, our other rational one, we probably won't see this one much, but I thought we would write it just in case. So again, x is in the denominator, can't divide by 0, so we have asymptotes here on the axis and here on the axis. And these wrap around as well, but everything's positive. So we're in the top right and top left. So positive y values only. But then our domain is the same. It's still going left forever, right forever, but it's not 0. So negative infinity to infinity, where x does not equal 0. And then our range, it's just going up forever. None of these are ever negative because we can't cross that x-axis. So we can just say from 0 to infinity. And you do want a parenthesis with the 0 because, again, it's never going to equal 0. It just gets super close. So then a polynomial, when you have x to the fourth, if you just graph x to the fourth, it looks really similar to a parabola, x squared. But if you notice, it's just kind of like flatter there in the middle. So it kind of goes like this. But it does cross 0, 0. And it just flattens out. But the thing about a polynomial is whatever your exponent is, that's the maximum number of times it can cross the x-axis. So when you have an x to the fourth, it could also look something like this. And more times than not, that's kind of what it looks like. So it's got those two little humps in the middle. But for our main one, the domain range is the same as the quadratic. So forever to the left and forever to the right. But then from 0 with a bracket to infinity. Okay, one more. So if we're looking at a square root, it also crosses at 0, 0. And it is the opposite of an x squared. So they're inverses of each other. So it's actually half of a parabola, but it's sideways. So it goes like this. And so with square root, it's always just going to be going in one direction. So this one is going to the right and it's going up. So our domain is from 0 to infinity. It starts at 0, just going to the right. And then our range, it starts at 0 and it just goes up. So 0 to infinity. Questions? Let's look at the back. Okay. Back here, this goes quicker. I know the front was a lot, but this isn't as bad. So these transformation rules are the same transformation rules that you have seen in every single math class since probably Math 1. I don't know if you do it in Math 1, but I know we started in Math 2. So hopefully you remember that f of x is the same thing as y. So when we're looking at these functions, I know it says like negative f of x, but that f of x just stands for whatever function that you're looking at. So if you're looking at an x squared, if you're looking at a square root, whatever you're looking at, that's what is in these f of x's. Okay. So our first one is when you have a negative out front of whatever it is. And so when that is the case, it is a vertical flip, which is a flip over the x-axis. So then the other one, which is when you have x on the inside of whatever, parentheses, absolute value, square root, whatever, and that is a horizontal flip. Or a flip over the y-axis. So if you have adding to the outside, anybody remember how that moves? Got like plus 2? Well, that's if it's on the inside. Yeah, it moves up. Good. So this one would move. So it moves up C units. So then how about minus C? Which way would it move? Probably the opposite of up, which is down. Yep. And again, C is going to be a constant number, so whatever number it is. And so that is if you have adding or subtracting on the outside of whatever your function is. So outside the parenthesis, outside square root, outside the absolute value, whatever. So then if it's on the inside, like these next ones, it's kind of the opposite of what you would think. So instead of plus being to the right, plus is actually to the left. And anytime that you're inside, you're always thinking about it like it's the opposite. And that's because it's kind of thinking about when you're solving for x. It's like if I solve this for x, I would say x plus c equals 0, and I would subtract c, and there it would become negative. And that's where that left and right kind of comes from. So then if it's a minus, that's to the right. Okay. So these last four are when you have a multiplication. So a number multiplied by the x or multiplied by the whole thing. And these are going to be stretches or shrinks. So the first one is when you have a number out front that's greater than 1. And so 2, 3, 1.5, 1.2, whatever, but it's greater than 1. And when that is the case, it is a vertical stretch. And so what that looks like is if you look, the blue one is our original parabola. The green one is our 2x squared. So it took it and it literally just stretched it out. So it made it skinnier. So if it is less than 1, so if you have a number less than 1, then that is a vertical shrink. So if we look at those same ones, there's our original. The green one is 0.2 x squared. So it took it and it just squished it. So it made it wider. And so that's a vertical stretch or vertical shrink. So then when you have numbers inside of whatever you're talking about being multiplied, these are horizontal. And again, they're going to be the opposite. So if the number is greater than 1, it's a horizontal shrink. So if we look at them, again, the one in the middle, that's our original. The green was that vertical shrink. And so then the purple is a horizontal shrink. So if you think about it, it squishes it this way, so it kind of makes it skinnier. So a horizontal shrink and a vertical stretch kind of do the same thing. And then our last one's going to be a horizontal stretch. And that's when our number is less than 1. And so again, I keep saying the inside and the outside, but it's all different depending on the equation, but the rules are still the same. So changes to the outside of whatever you're talking about, parentheses, absolute value, square root, they affect the y values, which is why they are all vertical. And then changes to the inside, again, of whatever function you're looking at, affect the x values, which is why they're all horizontal. But you have to remember that they do the opposite of what you would normally think. And again, that's all about the solving. You know, when you're solving for x, you do the opposite to move everything to one side. And so that's why that happens. Questions? I know we haven't really done anything, but okay. So down here at the bottom, we are going to decide what our parent function would be, and we are going to say how did they move. So to figure out the parent function, what you want to do is look at, if you took all of your adding, subtraction, and multiplying away, what would you be left with? So if I took away my -2 and my +1, I would just be left with x to the third. So that would be my parent function. So my parent function is f of x equals x to the third. Okay, and so that just tells me what graph I am changing. Okay. So then if we use our rules, we have -2 inside of the parentheses. So if we look back up here, minus on the inside, minus on the inside is moving to the right. So this one is going to move to the right 2. And then what does a +1 do if it's on the outside? Up or down? Up. Good. So then it moves up 1. Now, if you don't already have the Desmos app, you can download it. Of course, you can use a Chromebook. But if you just wanted to check yourself, you could look. Here's our original, just x to the third. Here's our little special point, and we can see that this graph went to the right 2 and up 1. And there it is. So you can always check yourself by graphing them. Let's look at 2. So if we look at number 2, if I take away all of my little adding and multiplying and all that, I take away my -2, I took away my 4, what am I left with? An x, and what do those little bars mean? It's on the front of this paper if you don't know what it's called. Yeah, absolute value. Good. So our parent function is absolute value of x. So that is the graph that we are changing. And again, if you don't know, you can graph it. See what the shape is. If it's a V, it's absolute value. And so this one is kind of tricky. We have 3 different transformations going on. Can anybody tell me one of them? Yeah. So we know it's going to go left 4. So that takes care of what's on the inside. So then we're left with the -2. So your first instinct is, oh, -2, that's less than 1. But if you look up here at our rules, if it's a negative out front, that's actually going to be a vertical flip. So when you're deciding if it's a stretch or a shrink, you just want to look at the number, not the negative part. So the negative part is a vertical flip. And then the 2 is greater than 1, and it's on the outside of these absolute value bars. So that tells me that it is going to be a vertical stretch. Questions on that? How about 3? What's my parent function going to be? If I take away the negative and the 4, what do I have left? Yeah, absolute values. So absolute value of x is my parent function. And then I have 2 transformations. Anybody want to tell me what they might be? So we have a little negative. Again, it's on the outside. So that's going to be a vertical flip. So since it's not adding or subtracting, that's going to be either a stretch or a shrink. So then it's inside. Yeah, good. So it's going to be a horizontal shrink because it is greater than 1. Yep. Y'all remember doing this before? Yes. Okay. I was got 4. So 4, again, we want to find the parent function. We take away the 1/3, we take away the 1 and the 5, and what do we have left? Anybody? Any guesses? What's it called when you got something over top this little thingy right here? Yeah. So our parent function is the square root of x. And then again, we got 3 things going on. We have the 1/3. It's on the outside. It's smaller than 1. So I look up here. Outside, smaller than 1, is a vertical shrink. How about if I have subtracting on the inside? So again, I find inside. Subtracting, so that one's moving to the right. 1. And how about subtracting on the outside?
Excuse me, please. Can I have a line of price ready to go?
Yes.
Thank you.
Uh-huh. Okay, so then minus on the outside is down 5. Okay, so our last 2 are a little bit different because they are exponential. So you don't have like a inside of parenthesis or inside absolute value. So the inside is what is inside the exponent. So you always want to think inside is what's happening to the x. And then the other thing that you don't really have to worry about is the 3. So I told you on the front that if it was an exponential, I just use an a. So whatever that number is your parent function. So in this one, it's a 3. So our parent function is f of x equals 3 to the x. So if it's an exponential, whatever that base number is your parent function. And so it's not a stretch or a shrink or anything like that. It's just the graph that you're changing. So the only things we have to worry about as far as transformations are the plus 7 and the plus 2. Which, how does that plus 7 move? If it's inside. Left or right? Get left. So left 7. And how about plus 2 on the outside? Up or down? Good. Up 2. Okay. So then our last one, again, same as 5. It's an exponential. So the 2 is just the base. It's not a change. It's not a transformation. So then the parent function is just f of x equals 2 to the x. So if it's an exponential, no matter what that number is, that's part of your parent function. It's not a transformation. So then the only thing that's different on this one is it has that little negative. And so the negative is inside the exponent. So if we look up top, a negative on the inside is a horizontal flip. So again, when you're thinking about inside and outside, you're looking at, is it happening to the x directly or not? Questions?